let me start. I will, just like Irakli on Monday, I will start with some recollections on classical Mackey functors, and then I will just pass to a higher categorified version, different from spectral Mackey functors. But we'll start the same way. So we fix a finite group G, and I call it G naught because later I will look at the more global versions of this, so I don't want to confuse the two. Sorry for that. So I will look at G naught sets, and so on. We fix a commutative ring of coefficients that are called K. And usually, well, it could be the integers, or it could be a nice local ring, or a field, pretty much anything. And then, well, what is an ordinary, a classical K-linear G naught Mackey functor M? As you know, for sure, there are many ways of seeing this, many possible definitions, all equivalent. So the original definition, which I think is first, at least implicitly, appeared in an article by Green in 1971 as part of the definition of a Green functor. So it's just a family of K modules, M of G, and you have one for every subgroup G of G naught. And then you have this restriction, induction, and conjugation K-linear maps between these modules. And then, well, they have to satisfy many relations. You have a functoriality, commutativity, and the Mackey formula that gives a name to this structure tells you how to commute, so to speak, induction and restriction. But there is a better point of view, which I like to call the motivic definition in terms of spans. I hope that the reason for which I call this the motivic definition will be clearer. If you don't agree with this terminology, it's fine, but I have a reason for this. Due to Dress and Linder. So, well, in this point of view, a Mackey functor is simply a K-linear functor, M, with values in K modules, defined over some span category. And more precisely, I'm going to take the K-linearized category of spans of G naught sets. So the definition, precise definition is here. So the objects are finite left G naught sets. The home modules are, well, I extend scalars to the coefficient ring K, but first, a priori, I only have an abelian monoid of maps, which are, these maps are isomorphism classes of spans of equivariant maps between the G naught sets. So these isomorphisms are just the evident isomorphisms of diagrams, which fix source and target. And then I compose via pullbacks of G naught sets in the evident way. So that's a nice source category, and this motivic point of view is nice because then, as I think Jesper said on Tuesday, then you just have a functor category, and you don't have a complicated machine with lots of weird relations. All the relations are pushed in the source, and so you can study that essentially small K-linear category directly. So, all right, now, what are cohomological Mackey functors? Because I want to focus on this for this talk. Well, the classical definition is very easy. So a Mackey functor is cohomological if it satisfies some extra relations, namely if you restrict from some group to a subgroup and then you induce backup, then it should be the same as multiplication by the index. So this is a relation between two maps from M of G to M of G, and it should hold for all subgroup inclusions for two subgroups of G naught. Okay, so that's my definition. It's quite elementary. So, for example, where the name comes from, well, from this example, from group cohomology. So if you have any K G naught module, any representation of the top group, then you can restrict it down to all the subgroups, and then you take homology, any fixed n if you want, or a graded thing, and then you have the typical cohomological Mackey functor. And well, in fact, there are variants. You can look at also homology, and then you can combine them. Look at Tate cohomology. You can look at H0, then you have the fixed point functors. And in some sense, they're all like that because you can use these to resolve. So these give you projective resolutions for all cohomological Mackey functors. So they are of this kind. So some non-examples also. Well, the Bernstein ring that we already saw, which is, for example, it comes up centrally in equivariant stable homotopy. That's not cohomological, but also some more like representation theoretic examples are not. Typically, if you look at the representation ring or the complex character ring, then that's not cohomological either. Okay, let's keep that in mind for later. So now the question is, okay, so the cohomological relations are useful in practice, but what do they mean conceptually? Where do they come from? Do we have a better way to understand these? And the answer is yes, that's the content of Yoshida's theorem. At least that's how I understand it. So let's recall what that means. So I want to look at this particular category. So inside finitely generated KG0 modules, I look at the permutation modules, okay? Those which have an invariant basis under the action of the group. And that's a nice full subcategory. And what I do is first I should do this observation, which is, well, it's not hard, but you have to have the idea, I guess. There exists a full, maybe full is the only non-obvious part of this. There is a full, essentially subjective k-linear functor, and it's also a tensor functor, but unfortunately, today I will not talk about the tensor side of things, except for now. But you have this nice functor, which I like to call the Yoshida functor, or Yoshi, so that in 10 slides time you will remember about it. But actually it should be called just linearization, because what it does is you take a span of G0 sets, and then you do the only thing you can do to get a linear map between the permutation modules associated to X and Y. So it sends a G0 set X to the free K module with induced action, and same for Y. And then the linear map is just sum over pre-images. So basically you take on the basis, you take a small x in big X, you take the pre-image under alpha, and then you sum after applying beta over the whole pre-image. So that's that formula. And it's really the only thing you can do if you think about it. It's even physicists use this in some contexts. So let's see how we can use this observation. The theorem says, so this is a reformulation of Yoshida's theorem, because at the time he didn't formulate it like that, but I think Panchacharm, and Street in their 2007 article put it first this way explicitly. Namely, the theorem says a Mackey functor M is cohomological if and only if it factors, and then obviously in a unique way if it does so, because this is a full and essentially subjective functor, through this functor, through Yoshida's functor. So an equivalent way of saying that, if you only look at the motivic side of things, if you only look at the sources of Mackey functors, it means that the kernel map of Yoshida's functor as a k-linear ideal of maps is generated, entirely generated by the cohomological relations, which are, of course, the span incarnation of the relations we saw before, namely the span associated to restriction, which is this one, composed with the span associated to induction, has to give a multiplication by the index. Okay? So that's very nice, because essentially what it says is that a cohomological Mackey functor is just one that factors through this linearization, or it's the same thing as a representation of the permutation module category. All right? Or people also formulate this in terms of the Hecke algebra. So of course, using some small Morita equivalents, you can talk about algebras instead of small categories. All right, so that's the classical side of things. Now let's categorify. Let's talk about Mackie-2 functors. So the idea is quite easy. And then, of course, you can decline it in many ways. So I'll tell you how I do that. By the way, most of what I tell you here is joint work with Paul Balmer. At the end, I will give you some references. So the naive idea is that we want to axiomatize something that happens a lot, namely when you have some families of k-linear categories, M of G, associated to finite groups G. They come together with restriction, induction, and conjugation functors, k-linear functors between them, and possibly other kinds of functors, like, for example, inflation functors that I will always assume we have also. And they should satisfy the most basic relations. You should require these because they come up in all examples, at least when finite groups are concerned. Namely, we want adjunctions between these functors. And we want such coherent isomorphisms which will categorify the various axioms of a Mackie functor. There won't be equalities between compositions of functors. There will be isomorphisms, and you want them to be somehow coherent, right? So the actual axioms that I'm going to use, these are, so there are many possibilities, I guess. So of course, we are inspired by the ordinary Mackie functors in the sense that if you apply K0, the additive K0 of additive categories, then to one of our Mackie-2 functors, you should get back an ordinary Mackie functor, okay? So by decategorifying in the usual way a Mackie-2 functor, you should get a Mackie-1 functor. And then on the other hand, our axiomatization is very close to derivators, more precisely additive derivators. So it's that kind of mathematics we do. And there is also this similar theory, which I see from this conference. This is quite fashionable now. This notion of Mackie functors in the infinity one categorical sense due to Barwick and many collaborators. But maybe I should tell you, that's why I prepared it here, what the difference is. So Barwick wants to work with infinity categories, so he captures all the higher coherencies, and he can talk about spectra valued Mackie functors and so on in an enriched sense. But we only want to stop at the second dimension, but we also want non-invertible two cells, okay? So we work with two categories, not necessarily with 2-1 categories. Because we want to model the adjunctions also directly without having to do extra work. All right. So what is the actual definition? Well, I need some two categories. I need the two category of finite groupoids, functors between them, and natural isomorphisms. And also a target, which will be the two category of all possibly large additive k-linear categories. So everything is k-linear, but I also want direct sums. That's why I say additive. And then I take k-linear functors between them and natural transformations. Then the definition. So the date here is 2020 because that's the published date, but they've been around for, I think now, 4 years at least. So a k-linear Mackie-2 functor is a two functor, a strict two functor, like with derivators, we can work strictly mostly. M defined on groupoids. It's contravariant on one cells because I want to talk about restriction functors especially. And then it takes values in additive k-linear categories. And of course, it has to satisfy some axioms. And the axioms are, well, you have additivity, which says that disjoint union or coproduct of groupoids is sent to a product of additive categories. And I say product, but it's actually also a coproduct in add k, dark sum. And then it follows that the empty groupoid goes to the 0 category. That's additivity. I want induction functors. So I want that every restriction I upper star, so the image under my two functor of I for every faithful functor I between groupoids, I wanted to admit both a left adjoint I lower shriek and a right adjoint I lower star. So I have induction and coinduction. I want them to satisfy a base change formula, which is the nice canonical incarnation of the Mackey formula here. So the left and right adjunction satisfy each base change with respect to pseudo pullbacks of groupoids. And then I want, so if you look at it, the first three axioms, if you know about derivators, the first three axioms are in common with additive derivators, if I restrict from diagram categories to groupoids, finite groupoids. But there is one axiom missing and one more. So the extra axiom here is ambidexterity, which says that there exists an isomorphism between the left adjoint and the right adjoint for every faithful I. So induction and coinduction have to coincide. Now, all right, let me comment a bit. Maybe with such an audience, it's not really necessary to make these comments, but I'll do them nonetheless. Let me explain a bit. So the additivity axiom, as we already observed once this week, groupoids decompose up to equivalence into groups. So it's easy to see that the data of the two functor M is entirely determined by what it does to groups and group homomorphisms and the conjugation relations between them. So the reason I talk about groupoids is because, for example, the Mackey formula is easier and more canonical to write, but the data is determined by groups. Then about the second axiom, so just like for derivators, I don't want to put induction and coinduction as part of the data. I just want it to exist. It makes things easier. But ambidexterity, notice that I ask some isomorphism to exist between every left and right adjoint. So it's easy to check in the examples, right? You see if there is one or not. But luckily, there is a nice fact here, what we call the rectification theorem, that says under these axioms, so if there are such isomorphisms, then there exists also a unique canonical isomorphism, which we can give a name, like theta I, between the left and right adjoint, I lower shriek and I lower star. And these are fully compatible with the given, with whatever left and right adjunction you are using. So given left and right adjunctions for every I, there exists unique theta I, which are compatible in a very good way. I don't want to specify, but you can always assume that you have this canonical isomorphism, which corresponds a bit, I guess, if you're used to it in equivariant homotopy theory, it would be the Witt-Müller isomorphism, which is a nice one. It's just not any isomorphism between induction and coinduction. So then you have variations of these axioms. Let me just mention for those.
Can I ask a quick question?
Sure.
Sorry for interrupting. That isomorphism, that ambidexterity, requires that I is fully faithful.
No. I should no. Only faithful is enough.
Faithful.
Yeah.
Faithful. Yes. And when I is an arbitrary functor, is there at least a morphism?
Well, I don't assume adjoints to exist when I is an arbitrary functor, because I think it's much more difficult to axiomatize what happens when you have inflation and okay, you know, the co-inflation or whatever. You will not have such isomorphisms in general. So yes. I don't want to. It's a more complicated story that I haven't.
Well, not isomorphism, but a morphism.
Yes.
Yes.
I think so, because these are pointed categories, and then you have left and can extensions. At least, you know, in the examples, you can always construct a natural isomorphism that compares them. Sometimes this is called the norm map in some contexts, and it will not be invertible in general.
Okay, thank you.
No problem. So I was saying that you can variate a bit the axioms. So I will tell you just as a reassurance that you know, there are many parameters here you can adjust to whatever needs. Namely, the definition I just gave shouldn't actually be called a Mackey functor, should be called more like inflation two functors, because we have restrictions along non-faithful maps of groupoids. We don't have adjoints, but we have the restrictions. So these are called inflations if you are talking about a quotient map of groups F. So if you want the proper global Mackey functor analog, then you should replace finite groupoids by finite groupoids where you only allow faithful functors. And some examples are only defined on that, as we will see. And then if you want, just like when we started this talk, if you want the local version of Mackey functors, the original one, for a fixed group G0, then you should replace groupoids with groupoids and faithful functors, comma, 2 category over your fixed group G0. That's a 2 category. It's proper thing to do here. It turns out that actually this is equivalent to an ordinary category, that of G0 sets, finite left G0 sets. And this is how, if you've never done this observation, that's why I put the exclamation mark, because the first time you see this, maybe you're happy because you realize, oh, that's why G sets come up, even if you're only interested, I don't know. That might ring some bells or enlighten some people, enlighten me at some point. All right, so let's see examples quickly. I mean, just to convince you that there are examples over the place. I will tell you that there is a Mackey-2 functor M for each of the following families of abelian or triangulated categories, M of G, depending on finite groups G. So you have examples, of course, in representation theory, or maybe I should say linear representation theory over vector spaces or modules. M of G could be, finitely generated KG modules, or the full abelian category, or the derived category, or maybe you can bound it to, you can take the stable module category. That's an example that's only defined here. You don't have inflation functors here. And you can decorate your categories as long as your induction restrictions are defined, then you have an example. The axioms are easy to check. In topology, you have a prominent example, the homotopy category of genuine G spectra, or a finite group G. If you vary G, you get such a structure. It's not too hard to see, but for example, for the ambidexterity, you need the Wirth-Muller isomorphism, which is an unobvious result, right? But once you have it, then it gives you the fourth axiom. So that's a nice example. This is where I come from, rather. In non-commutative geometry or non-commutative topology, you have the Kasparov, equivariant Kasparov category of a finite group, or the Hickson-Cons E theory, where the objects are sister algebras. So you can also do that. Or, and a nice example that I really like, in geometry. So this is an example which is defined locally for a fixed G0. So if you have X, some locally ring space, it could be a scheme or an analytic, complex analytic space, whatever, with an action of your group, then for every subgroup, you can, G, you can look at G equivariant sheaves over this space, sheaves of OX modules, and then you get a nice abelian category, and that gives an example. Or you can vary it, you can take the derived category of sheaves, or you can limit yourself to constructible sheaves, or if you have a scheme, an Arthurian scheme, to coherent sheaves, and so on. So you have all these various families of more geometric examples. And then you can go on all day giving examples, but we will not. Okay, so, all right. There is a motivic approach here too, which is relevant for my talk today. So that's it's a theorem now, it's not so obvious to prove. There exists, I should have said, so this is joint with Paul Balmer. So there exists a K-linear 2 category, mod K, of so-called Mackey 2 motifs. That's what we like to call them. So you might ask, okay, what is a K-linear 2 category? Well, it's the obvious thing. So you want the home categories of these 2 categories to be K-linear. You want the horizontal composition functors to be K-linear in each variable. And then maybe you want also direct sums of objects. In this case, they are given by in the end by the joint unions of groupoids. So I would say that's the evident notion of a K-linear two-category. Then what does it do? Well, through this two-category factors every K-linear Mackey functor. Namely, there exists like an embedding, in fact, of groupoids, a contravariant embedding of groupoids into this motivic two-category. And then for every Mackey two functor, there exists a unique extension, well, up to isomorphism, of course, a unique extension of these two functor to Mackey two motifs, and it will be a K-linear two functor, meaning on each home category you have a K-linear functor in the usual sense. And by the way, there are no extra properties. These are just K-linear two functors which correspond to Mackey two functors. Okay, so this correspondence is very similar to the Dress-Lindner picture of ordinary Mackey functors with respect to the classical definition with all the relations and the existence of induction and stuff like that. Of course, what we've done is we have pushed the existence of the induction functors into the source. Okay, so not obvious, but you can do it, and there are various models of this that I will talk about. So, all right, maybe I will say that when I send a finite group or a finite groupoid into motifs, I should talk about the motif of G, but I will call it G. I want to have extra notations here for nothing. And a corollary, it's something that maybe justifies a bit the adjective motivic here. That if you have, say, a finite group G, you can put it inside this two category of motifs, and then it has an identity, one cell, which has a K-algebra endomorphism, right? These are two cells from the identity to the identity of G. It's a ring, it's a K-algebra. And what happens is that for every K-linear Mackey two functor, you can apply this M hat. And so this ring acts on the category M of G. For every M, you fix G, and this endomorphism ring for G acts on M of G for every M. And for instance, as a consequence, in particular, if you have, sorry, I heard something, somebody trying to speak? No. So in particular, if you have a ring decomposition of this ring, let's say if you can write the identity as a sum of orthogonal idempotent elements, this is a commutative ring, by the way, you apply your M hat, and then you get, of course, corresponding decomposition as a direct sum, as a Cartesian product of the additive category M of G. Okay, so this starts to become interesting. So we want to study this endomorphism ring maybe. And the good news is you can compute with Mackey two motifs. We have concrete models for this. So,
Ivo, can I ask a philosophical question? Because like you
sure.
compared your approach to Clark's and others' approach. So you were mentioning there that you actually going to consider non-invertible two cells.
Yes.
Is this the place where you are sort of doing that, or?
Yes, exactly. So exactly. Of course, within groupoids, you don't have any because it's a 2-1 category.
Exactly.
But in the target, in the two category of additive linear categories, I have non-invertible natural transformations, right? And if I push them, if I push the units and co-units of the adjunctions into the source, then I get some extra cells, two cells, which partake in this motivic world. So the non-invertible two cells are all somehow generated by units and co-units of these two adjunctions, of the left and right adjunctions, by construction, because of the universal property.
So since Irakli asked this, maybe let me add in at this point and ask, so would you would you have an infinity 2 category of motives? You know,
Yes.
if you formulate it, and then it would also uniquely factor over that infinity 2 category as an infinity 2 functor?
Yes. So how to say, ideally, somebody should write down a theory which unifies Barwick's theory and our theory by working with infinity 2 categories.
Okay, thanks. Mm-hmm.
For sure, I expect that to be possible. Okay, so later we'll see a concrete model for this motivic 2 category, but just for now, I want to say that you can use it to compute, and one thing you can compute is this endomorphism ring. This is due to Paul Balmer and me, but with a crucial input by Serge Bouc, who actually told us, oh, I think I've seen this before. So it turns out that this mysterious universal ring of 2 cells is isomorphic to something which was known before and which is due to Yoshida, the same Yoshida as Yoshida's theorem, but in a different article. Something which is called the crossed Burnside K algebra. So it can be written like that. Sorry, there's a baby crying. I think it's my daughter, but it's distracting. Sorry. The Burnside, the cross Burnside K algebra is defined like this. So first you take you take G sets, finite left G sets, and you take the comma category over G together with the conjugation G action. And then you take the K0 group with respect to the disjoint union in the comma category. And then it's a ring because there is a certain braided tensor structure, which comes from the group operation, which is equivalent for the conjugation action. So you can work out as an exercise how this works. So you have a ring, and then you extend scalars to K. So that's what Yoshida does. And in fact, you have a very concrete description of that, just like for the ordinary Burnside ring, which works like this. So more concretely, this is a finite free K module generated by the G conjugacy classes of pairs HA, where H is a finite subgroup of the finite group G, and A is an element of the centralizer of H in G. And then the multiplication you can work out is given by this typically ugly formula with double cosets. And it turns out to be commutative because you have a braiding here, although it's not obvious to see directly. So it's a concrete finite rank free module with a certain multiplication. And it acts on M of G for every Mackey-2 functor M. All right, so let's give you an example. This is what I talked about 3 years ago in my other talk about similar things. I talked about this in more detail. So let me just give it as an example here. With K, just the ring of integers, let's consider the example from genuine G spectra. So M of G now is the homotopic category of G spectra. And we know, so everybody knows that the Bernstein ring BOG acts on this category because it's the endomorphism ring of the sphere spectrum, which is the tensor unit of the smash product, right? So that gives you a splitting of G spectra according to the idempotence in BG. But now we have a bigger ring, the Burnside, the cross Burnside ring, which contains, as I retract the Burnside ring, it has more primitive idempotence, and they act on the category. So you have a priori finer decomposition of the homotopy category according to the primitive idempotence of the cross Burnside ring. Now there is a small issue here. That would be a wonderful result, except that I don't know when this is 0. This could be 0, right? So in the other talk, I worked a lot to explain how you can make sure that this is not 0 after you massage your category enough. But now I want to take a more conceptual approach. I want to say when some of these idempotents act as 0, for sure. I will say later. So this example could be a motivation for the rest of the talk in some sense. All right. So let's try to do cohomological Mackey-2 functors. Well, the definition we came up with recently took a while because it's not clear what one wants here, and it's not clear how to obtain it once you know what you want. But I think we have a nice idea here. So we call a Mackey-2 functor M cohomological if the following composite is simply multiplication by the index of H and G whenever you have a subgroup inclusion of H and G. What is this composite? Well, these are natural transformations. You have the unit of the right adjunction, the one for the right adjoint of restriction. And then you have the co-unit of the other adjunction, the one that involves the left adjoint of restriction. And then, of course, we have this canonical identification between left and right adjoints you can use here. So you can compose unit and co-unit. And we ask this composite to be multiplication by the index as a natural transformation. All right? That's just the definition. So let's give examples to show that there are interesting examples. All examples from representation theory satisfy this, and it's easy to see explicitly. You know, the module category, the derived category, the stable module category, and all the variations, the homotopy category of complexes, all that. But there are also examples from geometry, namely all those examples using equivariant sheaves, or the derived category, or the coherent equivariant sheaves in case of algebraic varieties, and so on. They all satisfy these, and it's also quite easy to see explicitly. I mean, once you have the CAN extensions that give you left and right adjoints, you can write down the unit included explicitly, and then you see the theta, you can actually identify it explicitly, and you see. But why? So, okay, we have examples, but why do we want this definition? What is it good for? Okay. Well, first of all, it's a source of ordinary cohomological Mackey functors. Because there is a theorem. Remember when I said that one of the motivations to have Mackey-2 functors is that when you decategorify them by applying K0, the Gorton deconstruction to all your value categories, you should get an ordinary Mackey functor. Well, there is another way to decategorify a Mackey-2 functor to obtain an ordinary Mackey functor, which is very nice. I call it home decategorification. It works like this. So if M is any Mackey-2 functor and you pick two objects, let's say U and V, in one of the value categories for a fixed G0, then you can restrict U and V to all the subgroups of G0. And what you get, if you take the home set, is an ordinary Mackey functor for the group G0. Okay, you send G to the home between the restricted objects. And the kicker here is that, I mean, the reason I mentioned this here is because if M is a cohomological Mackey-2 functor, if curly M is one of those that I just defined, then any of these home decategorifications will be an ordinary cohomological Mackey functor in the sense of the traditional sense. Of course, if you instead apply K0, that's not guaranteed, because I gave you an example. For example, if you look at this, maybe this, for a field K, you look at finitely generated KG modules, and you apply K0. That's your representation ring. That's not cohomological. So K0 decategorification does not guarantee that the cohomological property is preserved. But that's good because, well, what are the examples here? Look, cohomology. So if you look at...
Try to say that again, Ivo. So it's not preserved by...
Yes, so maybe I should say it here. Watch out that the K0 decategorification of M curly is not a cohomological ordinary Mackey functor in general, even if curly M is cohomological in this sense here.
Mm.
So that's, I'm just a warning that my terminology cohomological is with respect to this home decategorification that makes sense, not with respect to the more obvious K0 decategorification. Okay.
I see. Thanks.
Was just maybe that's one could think that, but it doesn't work. So an example of this thing, well, group cohomology is a home, right? So you have the trivial representation, V any other representation, and then, or maybe you can shift it, right, in the derived category, and then you can take M, the derived category, make it 2 function, which is cohomological. So you know that when you apply by the theorem, that when you apply a home decategorification, you get an ordinary cohomological Mackey functor, or if you take any X algebra or that kind. So it makes sense, right? But all right, very good. So what else can you do with this? You can get examples of cohomological Mackey functors in the usual sense, but what else can you do? Well, let me profit of this occasion to mention a result by my student who just finished his thesis. So he proved that if you have a cohomological Mackey-2 functor M, which is K-linear over some ZP algebra K for a prime P. So this means that, so what I want to say is that all the other prime numbers act invertibly on the value categories of curly M. And let's assume that its value categories are all idempotent complete. Then you can prove, he can prove, that curly M is actually a 2-sheaf in the P-local topology in a certain sense. That makes some conceptual sense, but let me be even more concrete. It means that you get such a formula that for every G, M of G can be reconstructed as a bilimit taken in K-linear categories and computed over the orbit category of P subgroups of G. So that's very similar to this. So Jesper, you mentioned this similar result for the stable module category using infinity categories, limits of infinity categories, and it looks the same, right? You told me about this in June's defense. I didn't know about, but it's a very similar result, only it works already at the level of 2 categories. And for any cohomological Mackey-2 functor with this mild hypothesis. All right? So, okay, but why these relations? So the cohomological relations are useful, as I hope I just demonstrated. But where do they come from? What is conceptually the meaning of these relations? Are they just some random relations that are satisfied by some examples, or do they have a meaning? And this is the main result of this talk. They have a deeper meaning. And it's the same as before. So it's Yoshida's theorem. These cohomological relations that define a cohomological Mackey-2 functor, in fact, they generate the kernel of a so-called of a linearization of spans. Again, now I will spend the rest of the time here explaining what this means. Okay, this is the meaning of the cohomological relations for Mackey-2 functors, and I think it's very nice. But I have to recall a concrete model of Mackey-2 motifs which uses spans. So it works like this. So the result is that the universal 2 category of Mackey motifs can be realized as follows. So it has a concrete model like this, where the objects are just finite groupoids. Or if you really want to think in terms of motifs, you should take maybe formal Semans in a certain way, what we call the block completion, but it's really not so important for today. So what are the one cells? The one cells, the one morphisms are spans of functors. On the nose, no identifications, just spans of functors between finite groupoids, where the right leg is faithful. This is a faithful functor because it encodes inductions or co-inductions, right? So what are 2 cells? That's where the tricky part comes. 2 morphisms, well, you have to k-linearize afterwards, but a priori it's an abelian monoid of isomorphism classes of diagrams of groupoids, and the diagrams look like that. So you have this span here, this span here, and that two morphism that goes like this is such a diagram of, it's a span of morphisms of spans, okay? That's the sense it makes. And then you compose these two cells vertically and horizontally just by taking pseudo pullbacks, or you can even work with isocomma squares, which are the canonical choices for pseudo pullbacks in groupoids. And so you can do it concretely and you can compute. It's complicated, but you can. And all right, so now I can express Yoshida's theorem, categorified version. So I need one more two category. Actually, it's a bi-category, but let's not make that difference for today. It doesn't really matter. So everybody knows that there is a bi-category of bimodules, right? You have rings, bimodules between rings, and equivalent, and bimodule maps, natural transformations. And inside there, you can look at a specific two-full sub-bicategory, where you only look at objects. Basically, you look at finite groupoids, or you k-linearize them somehow. Look at finite groupoids, and then you look at only permutation bimodules between them. So these are, so if you, what is a one cell from H to G? It's a functor like this, right? That's what I mean by a bimodule. And then you can look at those which are right free. That's what I do. This is what RF means. Namely, the action from the right, so the action of the source of H has to be free. If it's a group, you know what it means, and it's the same thing for a groupoid, essentially. So you have these, they are closed under horizontal composites of bimodules. So it forms a bicategory with equivariant maps. All right, so let's use this. Yoshida's theorem in our version says the following, that there is an equivalence of k-linear bicategories between the motivic bicategory, you can think of the span models, and if you mod out the cohomological relations, which happen at the level of two cells, right? You have this unit and co-unit, and then multiplication by the index, and so on. You extend that to an ideal of two cells. You have to use you have to horizontally compose with everything. So you have to generate something so that you again get a k-linear bicategory. And the k-linear bicategory you get is this of permutation bimodules which are right free. Or to be more precise, the functor, the pseudo functor that realizes this equivalence is linearization. So you have to linearize spans both at the level of one cells and of two cells in the only way that you can. Let me tell you what this way is. So if you have a span, right faithful span, which conveniently is also RF, a right faithful spans of functors goes to a bimodule, so a functor like that, which is simply, well, you take the representable bimodules, one covariant, the other contravariant, associated to I and F, and you take the coend, so you tensor product them, and then you take the free k-module level-wise. Okay, that's the obvious thing to do, and it works. And at the level of two cells, once you have done this at the level of one cells, then you have a span of natural transformations. One goes up, one goes down like this, and you take the same sum over per images homomorphism exactly like Yoshida did, or like in the Yoshi functor I defined before. All right, so you linearize one cell, you linearize two cells from the span world, you land into the bimodule world, and what happened is you killed exactly the cohomological relations. So another maybe nicer way to say all of this, a snappier way, is that a cohomological Mackey-2 functor M is the same as a key linear pseudo-functor defined on this specific bicategory of right-free permutation by module. Okay? You could have defined them like that. All right. So I think I have one more slide. Yes, I will profit of the remaining time to make a connection again with these block decompositions, these motivic decompositions I mentioned. So look again at this quotient pseudo-functor from the theorem. So before I mod out the cohomological relations, I have this well-defined pseudo-functor, this linearization from the motivic two category to the bimodule two category. And for every object G, for every finite group G, say, I can specialize these two functor and it gives me a map of rings, okay? Between endomorphism rings of G here and here. So it's a surjective map of rings because of the theorem, although it's not so obvious to see by hand. And it can be made explicit by the identification I mentioned before. So on the left-hand side, you have this crossed Bernstein algebra, which is the endomorphism ring of the identity one cell of G. On the right-hand side, it's a very easy exercise. You have the center of the group algebra of G, okay? So the endomorphisms at the level of bisets of the identity bimodule of G. So, and this map, I call it rho G for some reason. This ring map is very explicitly described by this formula. So you send a subgroup H and an element of the centralizer of H and G to this sum over cosets. So it's a priori, it's a very simple map, but it captures a lot of information. I will try to tell you now. It captures the relationship between motives, in our sense, Mackey-two motives, and blocks of representation theorists. So let me tell you some consequences to convince you that this is an interesting thing to look at. So for every cohomological Mackey-two functor, so we work with this fixed G now. So the value category M of G will split according to the usual blocks, right? Because now this ring acts on this category. So, because the action of this ring factors through rho G, right? So I can decompose M of G using the usual blocks of representation theory. And this it's kind of obvious when the whole group algebra acts on M of G in some of the examples, but it's not always true. So what I want to note is that the full group algebra doesn't always act on M of G, okay? I have examples where it's not obvious, it's not clear, and it probably does not. And then something even better happens. So for example, if your ring of coefficients is nice, if it's a complete local ring, for instance, a field, then the primitive idempotents lift along these maps by some very general criteria, because these are finitely generated free algebras over such a ring, right? And it's subjective. And so even though I cannot compute this map explicitly, it's not so easy, but you have this lifting of idempotents. So this means if you have a block, namely a primitive idempotent here, you can lift it. You find one here, or maybe several that map to this one, right? So you can apply this also to Mackey-two functors, which are not cohomological, but as soon as the coefficient ring is nice enough. So for instance, take your homotopy category of G spectra and massage it so that it becomes linear over some complete local ring. For example, not too hard to do, over the p-adic integers. Then you know that you have a splitting of the homotopy category, massaged homotopy category, over the usual blocks of the corresponding group algebra, right? Then of course, well, the same problem appears as before. We have to decide which of these blocks are non-zero. So the action is not so obvious to check. You have to maybe do some extra work to decide which of these factors are there actually. But then you get nice explicit decompositions which come from representation theory, and you can see them for G spectra, right? All right, so I think I will just stop here, even though I think I have another 2 minutes. So let me just thank you. And I will give you here the references. So this is the reference. Sorry, somebody wants to speak? I heard something. No? Just want to end by saying that this is the reference for the Yoshida result I just explained. But these are all the other references that exist so far about Mackey-2 functors. There's this monograph with Paul, and then a published article with Paul, my students preprint, and then a very recent preprint on the green functor side of things. So that's all that you can read if you're interested in this stuff. And so thank you for your attention. Oh, I see, Irakli, you raised your hand.
So I have a question because I just see now here green functors, you know, so.
Yeah.
So one of the, I mean, correct me if I'm wrong, maybe I misremember this, but one of the ways to think about cohomological Mackey functors is also modules over this constant Z green functor. Is that right?
Yes. So
is there some story like this also going on here, like in some ways? I mean, I do understand that maybe if we write out what that really is, maybe we are recovering that category which shows up in.
That's a very good question, and it's a very nice idea, which I don't know the answer of, but I would like to. Maybe for those who don't know, like there is something called so if you take H0 of G coefficient K, right? That's fixed points of the trivial representation. Well, it's actually an ordinary Mackey functor, which is a green functor, right? Usually doesn't have this name. Yeah. It's like this. This acts on all cohomological Mackey functors, and in fact, you can prove that a Mackey functor is cohomological even only if it admits an action of this, which then is unique. So something similar to that should hold when you consider. So I hope, I think there should be something like that comes from the universal property of this permutation by category, saying that a certain green 2 functor, a very easy one, maybe some kind of fixed point green 2 functor, acts on all Mackey functors which are cohomological. I think it should hold. I haven't written down the details, but so you would have to. So this is, I should say, this is the analog of monoidal derivators in this setting, and also of green functors. So you can imagine it's slightly. I mean, you have pseudomonoids like Karov in a certain linear symmetric monoidal 2 categories. So it's not completely obvious to check details in this setting.
But if you try out to like combinatorially write out, like for example in the ordinary case, what's a modulo of such a thing? Like we can combinatorially write out what's a modulo of Burnside ring. It's a Burnside Mackey functor. It's actual Mackey functor.
Yeah.
If you try to do this here, are we going to recover this category, this permutation category you were talking about?
I'm not sure.
Yeah. Okay.
So you're right. There should be. I mean, there should be some universal property of the specific green 2 functors, like there should be a Burnside green 2 functor and a fixed point green 2 functor whose modules are respectively all Mackey 2 functors and the cohomological ones. Yeah. So I know now, as you can see in this preprint, what a green 2 functor is, what a module over a green 2 functor is. But and I have candidates for these 2 universal guys, but I haven't checked if these equivalences hold. I think they do, but the article was already too long, so I didn't do it yet. It's super recent. It's not even on the archive yet. It's just on my homepage. I wanted to talk about this actually in this conference, but it was a bit too last minute. So
Great.
Too fresh.
Thank you. Thank you.
Thank you for the question. All right. I don't see if there is any other.
Can I ask a question also? So now you have these cohomological Mackie-2 functors and all the ones. Is there a hierarchy, sort of filtering, so sort of where the cohomological ones are the bottom layer, and you sort of have higher filters?
Yeah, that's a good point. I mean, in the ordinary Mackie functor theory, cohomological Mackie functors are considered the easy ones, right? So inside the abelian category of ordinary Mackie functors, you have a subcategory, full subcategory, which is cohomological ones. It's a reflective subcategory or a tensor subcategory, some kind of tensor ideal. And it homologically behaves much easier. So Serge Book once told me, if you have a conjecture about Mackie functors, check it on cohomological ones first and then see what happens, because it's easier to check things out. So in some sense, I expect something like this to be true here. The Mackie functors, which are, sorry, the Mackie-2 functors, which are cohomological, are kind of linear in some sense. So this should be easier. And I expect something, now maybe this is a bit wild, but I expect something along the lines of, if you have a DG module, a DG enhancement, rather than just an infinity category enhancement or something like that, for your Mackie-2 functor, then there's a good chance it is cohomological. Maybe it is. I think something like that should be true. Maybe DG enhancement, K-linear DG enhancement, maybe with some extra condition, and you should get the cohomological relation for free. So maybe in some sense, the hierarchy would say, okay, among all the Mackie-2 functors, the ones that are linear already at the level of enhancement should be cohomological. That's kind of a wild conjecture. I haven't really tried to.
But I mean,
something like that should be true.
You could also try to do something like, I don't know if this makes sense, but like to ask more and more relations like this. Is that anything sensible to do? Like to ask for, like, if for specific subgroups you have this cohomological condition, but for higher ones you don't, or something like this?
Well, I'm not sure. I don't know any example like that, because the cohomological relations come up because in your concretely, when you look at an example, you usually have a model behind. You compute with Can extensions these adjunctions, and they are easy. Like, I mean, that the fact that you have a faithful inclusion of groupoids with finite index, all over the place. It's like how to compute this basically by matrices, right? If things are linear. So it's the proof of the cohomological relations. It's kind of independent of the group. I think it depends on the nature of the formulas that give you the Can extensions. So somehow I don't expect to be useful to have only this for some groups. It's more about what sort of model you have behind your Mackie-2 functor that makes the cohomological relations come true.
So now I have one more question, because you made me curious by saying if there is an infinity categorical enhancement. So do you know that an example where there isn't, or do you even expect an example where you can't go to cut infinity, or
I don't expect
presentable?
I don't expect any example to exist where there isn't one, but I know some where there isn't currently one.
Which examples do you have in mind there?
The examples from KK theory, from sister algebras. There are enhancements, infinity categorical enhancements, nice ones, but not for the equivariant versions of these theories. Nobody has managed to write, or nobody has tried. I wanted to do it a long time ago, but I never managed to collect all the necessary details. So there are no models in the Quillen model sense. There are no infinity category enhancements for the G equivariant, even for finite groups version. I expect that to be possible, but at the moment, I don't know exactly how that would work.
All right, thanks.
But it's not an obstacle. I mean, I'm sure that the next student who looks at that will be able somehow to write down something that works. So the question is whether a DG enhancement exists, right? Whether you have an algebraic Mackie-2 functor.
Well, that we would only expect in the algebraic examples to exist, right?
Exactly,
So, yeah.
exactly. All right. Any other questions? Who is the moderator? Not me.
Let's thank the speaker again.
Thanks, Paul.